So if you've been paying close attention, you might wonder what happens to SO2 in the atmosphere during photochemical smog. So we know that smog is contained or composed of ozone, VOCs, and NOx species, but then also SOx species, where we've got SO2, SO3, H2SO4. What happens to that? We haven't talked about where that kind of comes in. So I guess the question is, what exactly does happen to SO2 in smog? Before we can answer that, we really should ask, where does SO2 even come from? And there's two primary answers to that. The first is coal. This is the major producer of CO2 emissions, is coal burning. And that's because about 1 to 6% of coal is this chemical pyrite, which contains sulfur, which upon combustion generates SO2 that's emitted into the atmosphere. The second one is another major energy source here in the United States, natural gas. So natural gas wells can sometimes contain actually more hydrogen sulfide than they contain methane. And so that hydrogen sulfide, after a combustion, generates SO2 that's liberated then into the atmosphere. Now, if we look at a bit of a breakdown of where SO2 emissions are primarily attributed to and the magnitude of sulfur dioxide emissions in the United States, at least, this is a graph from your text from 2006. And it shows that by and large, the majority of SO2 emissions come from electric generation, primarily coal-fired power plants. There's a couple another 20% or so comes from industrial combustion. And then the remaining minority percent comes from some from vehicles and some non-industrial processes. Now, this was in 2006, where the total US emissions of SO2 were about 13.3 million tons per year. If we look specifically at the electric generation, so power plants, what we'll notice is that we've actually made quite a bit of progress in the past 15 years. So in 2006, just from power plants, the SO2 emissions, which is about 71% of the total emissions, was about 9 million tons of SO2 released into the atmosphere, due to quite a bit of progress by power plants in installing kind of scrubbers that will remove SO2. And then and a lot of this progress is fueled by adherence to the Clean Air Act's acid rain program. But we'll notice that over the past about 13 or 14 years, from 9 million tons in 2006, we've decreased all the way to under 1 million tons of SO2 emissions from electric power plants here in the US. Now, okay, so we've got a source now for SO2 emissions, and certainly industrial centers sometimes occur in cities and thus contribute to the photochemical smog as well. But what happens to SO2 after it's emitted? So it depends a little bit on the atmosphere that the SO2 is contained in. So if we're in clean air or unpolluted air, or in air that might have maybe relatively high radical concentrations or ozone concentration, but is clear, there's no mist or clouds, no water vapor, or maybe low levels of nitrogen dioxide. So that gives us kind of clear air. What happens in that case is a normal oxidation process, just that's initiated like all other gas oxidation processes are, by reaction with hydroxyl radical. So SO2 here has two SO double bonds. If we follow down through our flow chart here, we've got a stable gas. We come to the point where where hydroxyl radical will add to this to generate a sulfur, this HOSO2 radical. And now we're at the radical phase. So now we've got a radical intermediate. We can follow through that flow chart. And the next step is very simple. We see that if we pull off this hydrogen, we can generate a sulfur oxygen double bond. And so that's what happens. O2 comes in and pulls off the hydrogen. We generate hydroperoxy radical and sulfur trioxide, which is now, again, a stable gas. And that's sort of shown here pictorially as well. You can see the new SO double bond we've generated. Then the last step of this process is just that SO3 will react fairly rapidly with water vapor, any water vapor in the air, to generate sulfuric acid vapor. And that sulfuric acid is the end process for this oxidation, but it is then breathed in if this occurs at ground level, or it becomes part of acid rain. And so if we have a large amount or a high level of SO2 in the air, we'll eventually generate a sizable level of sulfuric acid, which then contributes either to acid rain or just ground level pollution and contribution to that smog. Now, okay, that's for clear air, but in many cases when we're talking about smog, we're not talking about clear air, we're talking about really dirty and not clear air. And so what kind of happens in polluted air? Well, in polluted air, the process is a little bit different. One thing to note in polluted air is that the concentration of radicals is generally very high, particularly of hydroxyl radical is very high. And remember, hydroxyl radical initiates the oxidation processes. So if that concentration is high, there's a lot of reactions that are occurring all the time in air. And one thing that can happen is if the concentration of hydroxyl radicals becomes high, as it does in smog, because hydroxyl radical, remember, for VOC oxidation, it's not only a catalyst, it's also a product of those reactions. So when the hydroxyl radical concentration becomes high, we can actually get dimerization to form HOOH, or just hydrogen peroxide. And that's important here because often what also happens in polluted air is with all of the other species that are in the air, VOCs, NOx, NO2, the water vapor will congregate either naturally through a mist or a cloud just naturally in there, or if there's any water vapor, maybe it would normally form a cloud, but then it kind of congregates and aggregates due to all the other particulate matter in the air. So we form these airborne droplets. And when SO2 is emitted into that air that contains these droplets, it will dissolve into the water droplets that are airborne to form sulfurous acid, or just H2SO3. Now this H2SO3 is a moderately strong acid, and so in water it's going to dissociate with this equilibrium here to generate the bisulfite ion, or the bisulfite ion, and then the H+ ion. And here's where the second step occurs, with real oxidation up to sulfuric acid. So this bisulfate ion here can undergo oxidation with two different pathways, both of which are a direct result of air pollution. The first here is reaction with ozone. So we've generated a bunch of ozone in the air as well. Some of that ozone will dissolve into those water droplets, and you'll get direct reaction between the bisulfate ion and ozone, essentially just a transfer of an oxygen over to sulfur to generate the bisulfate ion and O2. So then from here, once we've got HSO4 minus, simple protonation of that generates sulfuric acid. This is simply the conjugate base of sulfuric acid. Alternatively, there's also, as we mentioned up above, a sizable concentration of hydrogen peroxide, and that hydrogen peroxide can dissolve into those water droplets and react again. And here we get a simple, again, oxygen atom transfer over to oxidize the bisulfite to the bisulfate anion, and you generate water as the byproduct of that oxidation reaction. And then both of these bisulfate ions are again just the conjugate base of sulfuric acid. A simple protonation of this generates sulfuric acid, which then either contributes to acid rain or is breathed in by everyone traveling through this polluted air. Now, here's just kind of a graphic illustrating this process for polluted air oxidation of SO2. So you first get dissolving of the SO2 into the water droplet that generates the sulfurous acid, or H2SO3. This, because it's a moderately strong acid, undergoes dissociation and generates the bisulfite ion, which then can undergo oxidation either with dissolved ozone or dissolved hydrogen peroxide to generate bisulfate, which upon combination with the remaining H+ can generate sulfuric acid. The result of all this is that these droplets, since they now contain a strong acid, have a pH of approximately 4.4, and then this is really the major contributor here, or a major contributor to acid rain. So in summary, these are kind of the two major pathways for sulfur dioxide oxidation. In clean air, we primarily undergo a hydroxyl radical initiated oxidation, followed then by O2 coming in, pulling off a hydrogen to generate SO3, which reacts with water to generate sulfuric acid. If we're in polluted atmospheres, the SO2 tends to dissolve in these water droplets, eventually forming the bisulfite ion, which then is oxidized by ozone or hydrogen peroxide.